Hey, good morning, everyone. I'm Brian Miller. I'm at the National Renewable Energy Lab. I've been working on microgrid since the 90s for the U.S. military and now do it for U.S. Department of Energy out here in Golden, Colorado. I'll talk to you some about our test beds and the research we're doing here at NREL, and specifically some of the hardware in the loop tests and experiments that we're doing, finally wrapping up in an example of Borrego Springs. So this is just a quick overview of what I'll talk about. There's a lot of material here. Feel free to get in touch with me if you need additional information about any of it. This is kind of our campus. You can see in the bottom part of the image, the building to the right is the Energy Systems Integration Facility where I'm sitting right now. So first, my personal definition of advanced microgrids versus traditional microgrids like the ones that I was telling you about for the military back in the 90s were basically just diesel-driven backup power systems. You could call them a microgrid, but not really an advanced microgrid. An advanced microgrid integrates more of the advanced distributed energy resource technologies that are becoming much more prevalent now, such as PV or battery storage or other variable types of generation that needs to be managed, as well as controllable loads. There's a lot more energy management systems now and dispatchable loads that we also consider DER within the microgrid. And then also advanced microgrids, unlike the traditional ones, don't just care about their downstream loads. They also care about upstream features, such as providing grid stabilization to support the entire grid during a disturbance, and also to provide economic benefits to help pay for these expensive pieces of equipment while they're grid connected, because they nearly always are. 90+% of the time they're grid connected, and we're trying to use the microgrid controllers and the microgrid itself to generate revenues to help pay for the equipment, as well as make it available for when we do have a grid contingency and we need to go into islanded mode. So the key differences in these distributed energy resources compared to if I was just designing them for a grid tie only situation, is the sizing and location to be within the microgrid area. In this case, I would run economic analysis and find, say, my optimal size of PV, battery energy storage power rating, and battery energy storage capacity. But for microgrid, I'll also look at islanded situation and possibly choose a different size. And then, of course, the DER is going to change to a different mode when it's islanded. A lot of times the PV is too large for a small diesel generator to handle the ramp rates and the changes, so that can be curtailed. Obviously, inverters that were grid following become grid forming when we go into islanded mode. And then obviously, if a battery is trying to generate revenue by playing arbitrage or markets, when the utility goes away, there is no utility, there is no market anymore. So it's going to completely change its mode and start managing power stability for the island itself. We might also shed some load. And the master microgrid controller is obviously the manager of all these changes. So we do a lot of that kind of work here at the Energy Systems Integration Facility. We call it the ESIF. It's where I work, and it's a really wonderful facility. The first wing of the building has all our research staff. In the middle is the high-performance computer, which is currently a 2 petaflop, and we're adding 8 more. And it's all a user facility, so it's open for any partners to come in and use it. It's already paid for by the U.S. government. And if you haven't already come out to visit us, a lot of you probably have, you can look online at nrel.gov/ESIF and get a virtual tour. And of course, you're welcome to come out and visit as well. But inside the back part of the building, the final wing, are a lot of different hardware test beds, including hardware in the loop and real-time platforms. There was a couple of years ago so many different partners and projects coming through that just using the whole building as a microgrid became kind of a bottleneck. So I've split it out 4 different ways and different scales of microgrid test beds. You can see here each test bed has a real-time simulation platform to model actual locations. So that could be the OPAL or RTDS or one of several other platforms, depending on usually the partner that's coming in. So if they have a file that they've already created that's in SimPower systems, then of course we would use the appropriate platform to be able to use that without porting it to a different platform, and vice versa. Also, all of the test beds have fully controllable AC sources, which we call grid simulators. Basically, it's just a giant AC amplifier that can take the small, 10-volt AC or less signal that comes out of the real-time platform, amplify it up to 480-volt nominal three-phase, which, the nominal, we can actually push it on up to 600 volts AC RMS, so that we can do the, greater than 1 per unit over voltage type testing. And then tie it to our hardware, power hardware in the loop. And then once we've achieved the results, the waveforms for the current will be imported back into the real-time platform to push or pull that amount of power or current at the appropriate point inside the real-time simulation. All of them have smart PV inverters, which means they're controllable, or have volt watt or volt var frequency watt type ramps in them. And then each of the different scales of microgrid testbeds we're using here have some different features to them. So the smaller one, for example, does have a grid forming inverter, but it's a single phase, more in tune for residential type research, whereas the hundreds of kilowatts and up all have three-phase, typical commercial scale kind of voltages, 480 volt nominal usually, once it's been converted through the inverters typically put out 300 something volts, and then there's an isolation transformer to get me to 480. Once we get up into the megawatt scale, at the whole building is now a 2 megawatt microgrid, and we can use it at 13,200 volts. And then, of course, up at our Wind Technology Center, we have what's actually a 19.99 megawatt system, including 115 kV lines that we can use hardware in the loop. And on the next slide here, this is what some of the test beds look like. See the Power Systems Integration Lab, that's where the commercial scale equipment is. And then the whole building on the bottom left is the ESIF. And we've got 2 megawatts controllable and a lot of different indoor and outdoor test areas where we have electric vehicles, PV arrays, a lot of batteries or battery simulators, which I'll talk about later, as well as the supercomputer. And then bottom right is the Wind Technology Center, which you can see better on the next slide. That's where we have the multi-megawatt wind turbines that we can do hardware in the loop. In the top right, you can kind of see the distribution layout. So there's 2 ring buses. One ring bus is tied to our local utility, which is Xcel Energy. But the other one's the more interesting one, the CGI, the controllable grid interface. So that's where I have full control over voltage and frequency. And you can see every asset has a dual breaker scheme where I can tie a wind turbine or a large battery or an energy storage system onto my controllable grid, which is, of course, driven by a real-time simulation platform. So we use all this equipment for collaborations. We have about 800 active partners right now. You can see there's a wide spread of academic, federal businesses. I'd say about 80% of our work is government, and the other is work for others or strategic partnerships. And there's a couple of different ways we do it. Strategic partnership is mainly where we provide technical services, and then CRADAs, or Cooperative Research and Development Agreements, is where we mix, our research and intellectual property with somebody else's, and that's all defined in the agreement before we get started. But here's kind of where we're going now with microgrids. The electrical operations of microgrids is, in my opinion, mature now, and the national labs don't really need to be working in that space. The people have it handled. So we're looking beyond that now, and we're looking mainly at the financial drivers and controllers, cybersecurity. So we've got a 3-tiered approach right now that we're doing for internally funded lab-directed research. You can see 1, 2, 3 on the slide, measuring resiliency metrics and the monetary value thereof. I'm going to talk more about that in the next slides. 2 is co-simulating power and realistic communication models. So that means not only we're using a real-time platform to model power flows, but we're also using a different simulation platform to provide actual Ethernet network traffic flows. So there's an actual packet that flows through, not actual hardware machines, but virtual machines that represent firewalls, switches, letting that Ethernet traffic mingle with other traffic for congestion purposes or for actual either unintentional or intentional security events. And then once we get all these results, all these microgrid test beds and real-time simulation platforms pumping out all this data, we're trying to find new ways to share that data and get it across, especially to non-technical audiences like decision makers and politicians. So we're working a lot in using the output from HIL testing to drive 3D or virtual reality visualizations where the human brain can easily understand what's going on, what's not working right, and what the values of microgrids and controllers mean to them. So first, I'll talk about the resiliency metrics. What I'm noticing is there's a difference between resiliency and reliability. Reliability is 80 kV, a lot of the metrics we're very used to, focusing on direct consequences of a power outage. But resiliency is, what it's looking like is it more tends to incur indirect costs, such as, loss of staff, employees, leaving the company or organization because something happened within the company. And it's not just, let's say, for a grocery store, the loss of the product. It's more, the loss of reputation, the indirect things, the loss of shareholder value in the company over long times. And we're seeing that this cost isn't linear. It exponentially increases as the outage persists into days and weeks. But we were into year 2 of this study now, and we're actually noticing that there's an initial cost. The very first second of a power outage has a fixed cost. Then it ramps up exponentially, but then what we've also noticed is that cost curve tends to knee off and flatten out once the damage has already been done. So we're developing these cost curves, and that'll enable us to assign a dollar value that changes over time as the outage persists, especially into days and weeks. I'm not talking minutes anymore. An interesting thing we recently completed was between MIT Lincoln Lab and NREL, we did the Microgrid Controller Innovation Challenge event, which actually developed some metrics, as you can see on this slide. We held 2 public focus groups, one with microgrid owners and one with microgrid controller vendors, to help us down select the proper key performance parameters, the metrics, that were the key ones, the must-haves versus the nice-to-haves, and then also the relative weighting between these different metrics. So what that allowed us to do is convert all of our test results into dollar figures. And I believe Scott may talk more about this, so I won't go into that right now. But basically, we had all the teams come out. They did a controller hardware in the loop test. The top 2 teams were then invited to come back for a power hardware in the loop test. And the team with the highest score won. And this is kind of what the model looks like. MIT called it Banshee. We added some features to it, which is that little node hanging off to the far right, which is a power hardware in the loop node, as well as made some upgrades throughout the model. And we're now calling it Ghost. This is a feeder model that can run on an OPAL. You'll need 12 cores to run it. It's got 3 substations. Each of the feeders has a variety of critical loads and non-critical loads and various DERs such as megawatt scale, turbines, CHP, battery energy storage, PV, and some very challenging loads as well, like 200 horsepower motors, which can be non-soft started. But this testing model is open source and it's available to you. We've got a publication coming out that describes the test that we did for Controller Innovation Challenge, and there will also be some videos that are still being worked on that actually guide you how to set this up in your own OPAL system or real-time platform and replicate our results. So this is kind of what the node for power hardware looks like. You see there's a variety of generators, energy storage systems, and PV, and some different tiered loads, which are critical and non-critical. The interesting point here is, we actually used a 250 kilowatt bidirectional energy storage system, a battery inverter. But we wanted to make that significant at the megawatt scale to the rest of the model. So we provided a 20-to-1 scaling factor between the real power hardware and the virtual environment, which is a really interesting trick you can play when you're doing hardware in the loop testing. And I'll talk more about that in relation to Borrego Springs later. The other key takeaway here is the chart on the left. You can see the test iterations as the vendors repeated testing on their microgrid controllers. But the interesting thing is, look where the 0 line is on the y-axis. You know, that's the dollar value aggregated for all of the different metrics. You don't actually get positive and start making revenue, you can see, until iterations up into the 20s and 30s. That concerns me because a lot of non-lab hardware-in-the-loop tested microgrids are being commissioned out in the field. I know they get tested a couple times during commissioning, and maybe there's a punch list and maybe one more test. But I'm worried that some of these might still be not living up to expectations and delivering actual performance in the real-world setting. The co-simulation I'm going to skip through a bit because that's more of a future work we're doing that I described, to take the results from these simulations and hardware test and do something like you see on the screen here, where a human can stand in a 3D environment and understand the system. This particular system that these gentlemen are looking at is the South Table Mountain campus here at NREL. This is kind of what the co-simulation would look like. It's combining, you know, so the power flow co-simulation platform could be real-time HIL. So you see the hardware in the loop down below it. But there's also co-simulation models. So the command and control and communications run in lockstep with that, just like a power hardware loop, but now think of it as a communication simulator in the loop and other higher level input management, setting up the incident, setting up the scenarios. So what we're expecting from that is to be able to, you know, run it once, get the results, visualize them, show someone what a typical microgrid does for you as a baseline. You know, within a couple minutes, they should understand it, and then run it again with some kind of change. So let's say a researcher at a university or a private industry has an idea for making it better. We'll run it, and then we can compare that versus the baseline, not only the power flows, but power quality and the corresponding communication control flows. So for example, let's say I do an example where a real-time pricing signal comes down. So that's the financial, the layer 3, which Syed was talking about. I'll see that percolate down into my communication system. And the screen, I should see some packets flowing, communicating that to the microgrid controller, and then the microgrid controller is going to change the dispatch of assets. I'll see those communication flows go out to the DERs, and then obviously when they start to respond to those command signals, I'll see power flows start to change. So everything is locked together, everything is codependent, and I want to see that in real time in less than a couple minutes and be able to understand all of these complex dynamics. And this is kind of what that's going to look like. We've got agreement from Marine Corps Air Station Miramar to let us use their microgrid as an example. I just have to obfuscate it a little bit to make it representative and not create any security incidents. You can see the arrow coming down to the bottom right, which is going to be the network simulator running at the same time with a power hardware in the loop simulator. Exporting that data over to 3D visualization lets us evaluate options, provide the results to decision makers. And then my stretch goal for this is to create another reference microgrid, kind of like the demonstration that Syed showed you, but for Miramar. So you can actually go in and play with Miramar on your own, make changes, run different simulations, change control algorithms, run it again, and perform research, just like we have reference microgrids for the IEEE multi-node models that everyone uses as a common frame of reference. And in future research, we're really looking into distributed autonomous controllers, so getting away from the centralized control and letting the devices think and communicate with themselves in an untrusted, non-secure environment. And then my holy grail, of course, is to plug and play self-reconfiguring power systems where we don't have to do a complex interconnection study every time we want to add a new DER, because we want to scale this massively to billions of devices, and it's just becoming non-feasible to do this each time I want to add a new inverter or battery somewhere in the system. There's a lot of real-world microgrids we've done. There's many, many, many of them. I'm just going to talk about one today, so let me skip down to that. Here's my email address if you do need to get in touch with me. It's just brian.miller@nrel.gov. So here's Borrego Springs. This is a whole community in the desert side of California, San Diego County, that has 4 megawatt average load, a 14 megawatt peak load. But they also have 26 megawatts of large-scale PV plus 6 megawatts of concentrated PV plus about another 2 megawatts of rooftop PV in the community. So it's much greater than 100% renewable. They also have large battery energy storage systems and diesel backup generators. They also have 3 different microgrids that they can set up. Microgrid 1 on the screen is the battery energy storage systems, the diesels, also not shown as a supercapacitor. But it feeds their critical circuit number 1. But they also have point of common coupling number 2, which can bring on a couple more circuits of load. And then the interesting one is point of common coupling number 3, or island 3, they call it, which actually brings on the 69 kV bus and allows me to factor in that 26 megawatt large-scale PV plant. Here's what it looks like in real life. And here's the different evaluation options we had. We could have done pure simulation, but the inverter models were a bit too ideal. We wanted to actually capture the real dynamics of the inverters. We did bring the microgrid controller out of the loop, which is option B, but we still had the inverters being too ideal. So we actually went with evaluation option C here, which is controller and power hardware in the loop testing. Option D, we could have done a full hardware build, but we couldn't have done all the circuits to accurately represent Borrego Springs, so it would have been oversimplified. So we chose option C as our best HIL option. And this is my final slide. So this is what we built in the lab and did the testing. Starting on the top left, you can see the Anderson 660 kilowatt bidirectional. It's basically a battery simulator. It's a fully controllable DC source, but that was tied to a Schneider battery energy storage system, and the hardware in the loop you can see couples down into the real-time platform at the bottom of the screen. And then in the top center you can see the large-scale PV. We used a MagnaPower to represent the PV DC side and fed that into an SMA Sunny Central 500 kilowatt commercial PV inverter, which is the exact same make, model, and firmware they're using in Borrego Springs. But of course, they have 26 megawatts, and we only had 1 unit of half a megawatt. So simply scaling factor between the real world and the virtual world of 52-fold basically means I had a 26 megawatt solar farm sitting in my lab to do this testing. Over on the right, you can see we also had the Spire Wave Commander, which is the master microgrid controller, and a couple diesel controllers, which were Woodwards. We interfaced those in a pretty special way because we didn't want to deal with high-level signals, so we actually changed the inputs to low-level so it could read directly off of the real-time simulator platform's output cards. And then the results we got were very interesting. We were able to do a lot of testing that's just not possible in the field, like incurring multiple power outages on the community, pushing their voltage way up above 1 per unit, changing the frequency far above and below 60 hertz. A lot of things that if I did that in Borrego Springs, I'd be in jail right now. But we were able to do multiple test iterations in the field, make improvements so that, our mission here at NREL is to encourage the widespread adoption of new energy technologies. And projects like this, if they went out in the field and they experienced difficulties, it would create a bad reputation. It would slow down that adoption. So that's the real advantage of doing hardware in the loop lab testing is to fix these things and make the projects more successful so that we can scale them out in the field. And with that, I'm going to turn it back over because I am out of time. But thank you very much, and please let me know if I can help out in any way.
Thank you very much for your presentation, Brian. It was really interesting.